So what we're going to do is now that you've actually learned about regression, you've seen it run, we're going to actually show you how to interpret it and walk you through an interpretation. We're going to do that and really kind of lay that out for you so that you're not only going to be able to do it for the first assignment, but also for your second assignment. As with any good piece of analysis that's statistical, we want to start with a set of hypotheses. And what we're looking at is we're going to look at the amount people pay in their first mortgage. And we're going to try to hypothesize about that among people in Michigan in 2020. And so the null hypothesis, remember, says there is nothing going on here. And in this case, because we're dealing with regression, we're looking at relationships. So we're going to say there is no relationship going on here. If it were ANOVA or t-test or chi-square, we'd say there is no difference. There's if we're thinking about the big four questions, this is, is there a relationship and how do we know? That's what we're looking at. So the null hypothesis is that there is no relationship. And if we find that to not be true, if we reject the null hypothesis, we have to suggest an alternative hypothesis, and that would be this one, that there is a relationship. Now the vernacular hypothesis is the one that says, how do I say this in English to the people in the room who know nothing about data analysis? That's what the vernacular hypothesis is about. And so, as plainly as you can, you say, we're investigating whether or not household income is related to the amount someone pays in their primary mortgage each month in Michigan during 2020. So that's what we're about. All right. I took a very large data set from IPUMS. I downloaded a bunch of variables. And from this, I needed to separate out some things. So I needed 2020, so I've got that. I needed Michigan, so I looked at the state FIPS code, and the state FIPS code for Michigan is 26, and I selected that out. I did two things with the home value. I wanted home values above 0, some homes that had at least some level of value. And then I needed to kind of eliminate the extra cases that where home value wasn't reported, and those are listed as 999, 9999. There are actually 7 nines in a row if you go look at the data set. I have 9990 for a reason, because sometimes there are other codes in there as well. I look at IPUMS and I look at the data description, and sometimes I'm like, you know what, there are 3 or 4 more codes below that 999999, and I just take 90 to just kind of eliminate those as well. So I did the same thing with income. I did the same thing with full-time income. And I'm hypothesizing for later that the amount of time someone travels to work might have an influence on it. That the further you travel to work, the higher your income is. And so I took travel times of people who travel to work. And because it's unlikely anyone owns a home that when they're less than 18, I took only people who were 18 and older. So that was my selection process. Now I ran just a single variable regression on mortgage payment and household income. And the mean mortgage payment was $763, and the mean household income was $124,000. I did find a relationship, right? The relationship is a small to moderate relationship. And so it's 0.34, R equals 0.34 in the Pearson correlation. And it is statistically significant. So if you look down at significance, it says less than 0.001. We're looking for things that are less than 0.005, and so it's statistically significant. So that's a good thing for us. But what we're really interested is does our regression model hold up? So I know that there's a relationship, but is that relationship explanatory? And so that's the next piece in this is this ANOVA piece tests whether or not your relationship really exists. And so what you're testing is you're testing this. You're testing whether or not there's a relationship or not. And if your test statistic turns out to reject the null, then you suggest the alternative. So what this ANOVA piece here does is it tests this. That's important to remember. All right. So F is your test statistic. The significance follows that. When you report that to me, you would report F equals 30.159. P is less than 0.001. P is less than 0.05. We're going to reject the null and suggest the alternative. That's how you write it. If you don't tell me what the test statistic is and you just tell me the p-value, I will send that back to you in a minute, just to make sure. And I stop reading at that point. I just send it back. And so you need to make sure you list the test statistic and the p-value. And the test statistic is going to differ with different pieces that we're going to do. All right. The next thing is, well, how good is it? Okay, you now established that you have a model, right? We rejected the null and we're suggesting the alternative, right? So we're suggesting this. And so the question is, how good is it? That 0.344 is the relationship of the model. So the model has a relationship. It's the same one you see here. When we add variables later on, it lumps them all together and tells you what that model is all together. Your R-squared tells you how much variation of that first mortgage payment that you're explaining. You are explaining 11.9%, which doesn't sound that great. But in business, remember that human behavior is notoriously difficult to predict. If you can explain that much of what's going on, you're actually explaining quite a lot. I tell students, if you're explaining 20% of what's going on in a regression model, you're probably making money hand over fist. Now, in other fields like chemistry and biology, that wouldn't hold water. I mean, the chemist used to take me in the back alley and just beat me up over this stuff. But in business, it works. The adjusted R-squared is a more conservative version of R-squared. I usually report that to the client just to be on the safe side. Sometimes, in this case, it's not varying very much. In some cases, it will. I think in our example later on, it will vary a little bit more. This next part, the coefficient, describes the relationship. Remember, when you rejected the null, you said there is a relationship. And now you've explained how big the relationship is. Here's where you explain what the relationship is. And so in this case, as household income increases by $1, the size of the mortgage increases by 0.2 of a cent. So where I get that from is this. Okay, so my dependent variable is mortgage payment, right? Household income is my independent variable. As household income increases by $1, this beta value here increases by that amount of what it's being measured in. In this case, 0.2 of a cent. Really, not very much, but still an increase, and it's a real increase. 0.34 is a standardized beta coefficient, and what we're looking for is not only is what this explains, but is it statistically significant and that it really is explanatory. In this case, what we look at is the t-value and the following p-value. You report that t is 5.4, p is less than 0.01. The variable is explanatory. If this t were much smaller and your p-value was above 0.05, you would throw this variable out and say it's not explanatory. So I want to make sure that you know that because you're going to run across variables that aren't explanatory, and you need to talk about this. I've largely ignored the constant, and I need to talk about it here really quick just so you know about it. It is a theoretical piece, and to be honest with you, if you go back to your algebra class in high school, it is the y-intercept of your analysis. So that if your household income is 0, the value of the mortgage payment is 463. In this case, because it's a single variable, it actually makes some sense. A lot of times if you have a more complex model, this doesn't make any sense. It's a mathematical construct. It's important to report but it's not important in terms of your interpretation, but I want to make sure you see it and you know that I'm not ignoring it when we go further. All right. It's a decent model, right? And it's not a bad model, but can we do better? And one of the things about regression analysis is you can add more variables to this, and sometimes you can add more variables and get a much better model. There's some things that you need to know that we're going to assume in our model. Number one, that there is a linear relationship, because not all relationships are linear, but we're going to assume that that's the case. We're going to assume that our variables are normal. We can do that through the central limit theorem. Little or no multicollinearity and no autocorrelation. Those are tricky pieces. And the question is, how do you know that? And right now, we don't know that. But we're going to find that out later on. So just so you know that we're going to do that. All right. So next, we need a more complex set of hypotheses. So the null hypothesis is that there isn't a relationship between the amount of money paid in a first mortgage and household income, the value of the house, usual hours worked, total personal income, total family income, and travel time to work in Michigan in 2020. Now, if you're paying attention and you actually, paying attention to some things, you'll note that this model has some problems already going out of the gate. And so what I want to make sure that you know is that I know that there are problems in this model. We're going to talk about them, but we're going to assume that we're naive here, and we're just going to say, oh, this looks good. And so you have the alternative hypothesis and you have the vernacular hypothesis. You can read those. All right. So I run the model, and I run a correlation matrix on all of these. And so the interesting thing about the correlation matrix is it will tell you what the relationship is. And so it'll tell you that mortgage and personal income, this is the relationship. Total family income, this is the relationship. It'll tell you whether that relationship is significant or not, and at what level it's significant. And so one of the things that I always do is I look and pick to see whether or not I've got some significant relationships. So here is a relationship between sex and mortgage payment. It doesn't seem to be significant, but it does seem to be significant in some other areas as well. So look for significant relationships when you're picking out your variables. You can go back to this slide later and look at it. What I'm going to do is just keep moving forward like I don't see it, because I want to show you some things. And basically also because I would make different choices here based on what this output is that I'm not making in this model, because I want to talk about a problematic model. All right. First things first, the descriptives. I get all of those. And those all look fairly in line. And remember, one of the most important things to do is to look at whether or not these are reasonable numbers. If you have numbers that don't look right, in other words, usual hours worked are like 90, you know you've probably got a filter running. If your house values are average house values are 3 million or higher, you probably fail to eliminate the 99999s. So check your filters. I mean, this is always a good place to check that. All right, so let's look at the model. And so the question then is the model significant or not? And so this is what it's going to tell us. So you're going to report that F equals 8.8, P is less than 0.01, P is less than 0.05, so you're going to reject the null and suggest the alternative. So you're going to suggest that there is a relationship going on here, and you're going to reject the notion that there is no relationship. And so now that you've determined there is a relationship, you have to describe it. And everything that follows is actually a description of that relationship. All right. How much are you explaining? So you've increased, the nice thing here is you've increased your R. You've got a much higher R, 0.49. So it's now a moderate relationship. and your R squared has increased to 24%. You've improved the model. You've even improved the adjusted R squared. But also now, look at, there's a real difference between the R squared and the adjusted R squared. So the more conservative estimate, says, there's some other things going on here, pay attention, but you've got a more conservative estimate of R squared here as well. Probably the one that I would use if I were going to talk to a client, particularly if there's that much difference between them. All right. So with that set, let's talk about these coefficients. So remember, for every 1 unit of the beta value, right? So for every 1 unit of household income, or house value, or usual hours worked, or total personal income, or family income, remember, for every 1 unit of this, the dependent variable changes by this amount. So for every 1 hour worked per week, the mortgage increases by $4.53. For every minute increase in travel time, mortgage decreases by $2.56. Contrary to what I was thinking, but nonetheless, it indicates what's going on in the relationship. And so one of the things is that you want to always make sure you know what you are, what you're looking at, and how that's working. All right. That explains that relationship. So the real question then is, are the variables explanatory or are they noise? And that's an important piece here, because if they're explanatory, great. If they're noise, we got to get rid of them. And so the T allows us to do that. And please note the following. What was a significant variable in when we were using it as 1 turns out to be not significant here. T is 0.618. P is 0.5, we would say that variable is now not explanatory. And as we go down these T's, house value is explanatory, usual hours worked is explanatory, is not explanatory. And what we find is we only have one explanatory variable, which is house value, which makes some sense that would work like that. But one of the things that you kind of look at and go, what happened to my model? And this model really stinks. And when your model stinks, there's some things to do. You switch out variables, you eliminate variables. We're going to do some elimination here in a minute. But I want to make sure that you know it's okay that your model stinks. You just have to tell me that. You don't have to find great results. You just have to explain the results you get. That's really the important piece. And if these are the results you get, you need to tell me this is not explanatory. That's fine. That works. Do that. All right. One of the things that we talked about earlier is collinearity, and you need to note that you have to pay attention to collinearity. So tolerance and VIF allow you to note collinearity. And so if your tolerance is smaller than 0.25, you probably have a problem. So you've got a problem here with family income, and you've got a problem here with household income. If your variance inflation factor is greater than 10, you probably have a problem. Big VIFs, okay? So what's probably happening is these two are probably collinear. And since we ran that model earlier and household income was explanatory, these are probably interfering with each other some way. Pull one of them. You don't have to pull them both, but pull one of them. Rerun the model, see what it looks like. Household income probably is going to come out just fine as an explanatory variable. So just so you know that going in. All right. We looked at collinearity, and so what I want you to think about is how you're going to revise the model. And so I revised the model and I said, you know what, I think I think household income is going to work. I think age and sex are going to work. I think older people will probably already have bigger mortgages, things like that. Still not good. That's okay. Explain that. Explain that it's not explanatory. That's just fine. That works just fine. I still have a significant model. Please note that household income now works. And so, travel time, that didn't pan out either. Basically, I've got a model that's not that good. Our first model was probably our best model. And so what I want you to do is I want you to note, you interpret this, you describe the relationship. And how I would describe this relationship is that household income seems to be a primary predictor of house value. And sometimes it works like this. And if you go back to the Walgreens video, one of the things that I asked Ben Farster, and Ben's a former student of mine, and so I asked Ben Farster, I said, when you were doing the flu index, and did you come up with all these great regression models based on products and things like that? And he said, yeah, we ran a bunch of them. And you know what? It turned out to be the one variable. It's a single variable regression. And so one of the things is sometimes the simple answer is the best answer. And one of the things that I would say is I use the term parsimonious. And I often use the term parsimonious a lot in class. If this is an in-person class, you hear me say, it's model parsimonious. And parsimonious is another word for simple. And you want to keep your regression models as simple as possible. In your assignment, I'm going to ask you to create in your assignment in week 2, I'm going to ask you to create a model that's somewhere between 3 and 6 variables. Simpler is better, right? I'd like a multiple regression, but you're going to need to tell me and be honest with me about how it works and how you might revise it. But that's coming in week 2. But for now, that's how you would interpret a regression model.